The next gas law is called Avogadro's law, and we are looking at volume and amount of gas, but really it's moles of the gas. So they have a direct relationship, and you can see that with this little guy blowing up a balloon. So when you start, before you start blowing up the balloon, you know it's flat, there's no volume, but as you begin to blow air into the balloon, the volume increases, but also the amount of gas you're blowing into the balloon increases as well. So there's a direct relationship there. So it has the same look, the equation has the same look as Charles' law. So we're just replacing, instead of temperature, we have moles. So we have V1 over N1 is equal to V2 over N2. Avogadro's law can be a little bit tricky. I'm going to show you why here in just a minute. But again, it has that direct relationship. So because it does, we have the same graph, the linear line for Avogadro's law as we did Charles' law. So volume is on the y, moles on the x, and as one increases, the other increases as well. So let's use our equation. So as we read through this problem, we see that it's only dealing with volume and moles, so we know it's going to be an Avogadro's law. And so let's read through that and fill out our numbers here. Okay, it says a 4.8 liter sample, so that's V1, contains 0.22 moles of helium. That's N1. And how many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? That's V2. So, whoops. We're solving for N2, but you have to be careful because it says how many additional moles. So underline that. How many additional moles? So the answer is not N2, it's the increase from N1 to N2 that we're going to be calculating. Okay, so we're going to be solving for N2. Okay, so here's N2. So again, if you want to rearrange the equation, you can. We've got to move N2 up here, and then we're going to move both of these. Oops. Okay. Why is it not working? We're going to move both of these over here, but we're going to switch them. So you're going to get N2 is equal to V2 times N1 divided by V1, like that. So N2 is equal to 6.4 liters times N1, which is 0.22 moles, divided by 4.8 liters. So liters cancels, and we get N2 is equal to 0.29 moles. But that's not our answer. Okay, that's just N2. So our answer is going to be how many additional moles are added. So we've got to subtract out what our initial was, so the 0.22. So that gives us 0.07 additional moles were added. So that's why I said these can be a little tricky, because there's an extra step you have to do. That doesn't happen with Boyle's, Charles, and combined gas law. That just happens with Avogadro's. Okay, now we're going to put Boyle's, Charles, Avogadro's law all together into the ideal gas law. So you can see kind of right there how they've put them together. We're just missing one thing. We're missing a constant, and that's what R is. Okay, R is the ideal gas constant, and it is equal to 0.0821. So the ideal gas law is PV equals nRT, and again, that's just putting all three of those gas laws together. So P times V, that's Boyle's law, right? They're inversely related. And then V equal to N, that's Avogadro's law. And then V equal to T, that's Charles' law. So everything comes together into this ideal gas equation. Okay, so since R is equal to 0.0821, liters times ATM divided by moles Kelvin, we have to look at those units, okay? So pressure is going to be in ATM. It has to be in ATM because R is in ATM. Volume is going to be in liters. That didn't work. Okay, because the R is in liters. And then N is moles. It's going to be in moles. So that's not changing. And then T has to be in Kelvin. So we have to pay attention to those units. Before it was just make sure the units match, no big deal. But now they have to specifically be in these units because that's what the R value is in. Okay, there's a couple of things here about the ideal gas equation. So first of all, the ideal gas equation is an equation of state. So all that means is before we were talking about, this was the initial set of conditions for the gas, then it went to this. So for the ideal gas equation, that's not what we're going to be looking at. The equation of state means we don't care where the gas was or where it's going. We only care what the conditions are at this moment. So what is the pressure? What is the volume? What is the moles? What is the temperature at this specific moment? So the word problem looks a little bit different. And then another thing is we make two assumptions for an ideal gas. And the two assumptions are, first of all, the molecules of the gas have no volume. So we know that gases take on the volume of their container. And so we are just assuming the molecules themselves here have no volume. And number two, the molecules do not interact. So those are the two assumptions for an ideal gas. Okay, let's put this equation to use right here. It says calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and a temperature of 315 Kelvin. So it specifically gives us volume, pressure, and temperature. Or no, I'm sorry, not volume. We're calculating volume. Moles, pressure, and temperature. So it's not giving us, this is what it was, this is where it's going. It's giving it right now what everything is. So we're going to plug it in. So again, you can still do like we've been doing and put everything off to the side. P1, or not P1, P, V, N, R, T. So R is always the same. And then, let's see, our moles is 0.845. And temperature is 315 Kelvin. And we're solving for volume, and the pressure is 1.37. So, I'm going to solve for volume. So you can rearrange the equation. Okay, so we're solving for volume, so all I have to do is move P under here. So V is equal to nRT over P. And before we plug our numbers in, we want to make sure our units match. So ATM is good, moles is good, Kelvin is good, so we can plug everything in. Okay, so moles we have 0.845 times 0.0821 times 315 divided by our pressure, and we get 16 liters for our volume. We can also use the ideal gas equation to solve for an unknown gas, so the molar mass of the unknown gas. So remember, molar mass is just grams per mole. So those are the two things we're going to need to be able to calculate molar mass. So in this question, it says a sample of gas has a mass of 0.136 grams. So there's our grams. Now we just need moles of the gas to be able to calculate molar mass. It says its volume is 0.112 liters at a temperature of 298 Kelvin and a pressure of 1.06 atm. So given that information, we can plug those numbers into PV equals nRT, solve for moles, and then take grams divided by moles. Okay, so our grams is 0.1136. Let's try that again. Oh, for goodness sake. Okay, there's our grams. So P, V, N, R, T. So all we're missing is N. It says we have 0.112 liters, pressure of 1.06 atm, and our temperature is 298 Kelvin. Okay, so to rearrange the equation, we just have to move R and V under, or not R and V, R and T under PV. And our units are all good, so we can plug everything in. Okay, so that gives us 4.85 10 to the negative 3 moles. Okay, so we have our grams, we have our moles. Now all we have to do is divide the two to get molar mass. And we find that our molar mass is going to be 28 grams per mole.